Welcome to a deep dive into OEIS A000330, a sequence known as the square pyramidal numbers.
A classic.
Our mission today, well, it's to unpack these numbers. They're fundamentally defined as the sum of the first n squares, so 0 squared up to n squared.
Right.
This gives us an intriguing series of terms, and for you number theory students out there, the elegant formula to calculate any term is n plus 1, 2n plus 1, 6.
And what's truly fascinating here, I think, is how these numbers visually represent the total items needed to build a pyramid with a square base.
Oh, okay.
Imagine stacking, say, cannonballs or even little cubes. A pyramid with just a 1-by-1 base needs, well, one item.
Makes sense.
Scale that up. A 2-by-2 base needs 1 plus 4, so 5 items.
Right, 1 squared plus 2 squared.
Exactly. And then a 3-by-3 base requires 1 plus 4 plus 9, which is 14 items. It's a literal, tangible manifestation of that formula we mentioned.
So the sequence starts as 0 is 0, a 1 is 1, a 2 is 5, a 3 is 14.
And so on. Yeah.
Wow, that visual of the stacking cannonballs, that's incredibly intuitive. But you're saying this isn't just about 3 dimensions.
No, not at all.
That the same sequence shows up when you're looking at something totally flat, like squares in a grid.
Precisely. And here's where A000330 really shows its versatility. The geometric interpretation extends beautifully to two-dimensional arrangements.
How does that work?
Well, if you take an n by n square grid, an actually tells you the total number of squares of any size as long as their sides are parallel to the axis that you can find within it.
Oh, interesting. Not just the small ones.
No, all of them. So a simple 1-by-1 grid just contains one square, obviously.
Okay.
But a 2-by-2 grid, well, you've got the 4 1-by-1s and the one big 2-by-2. So that's 5 squares in total.
Ah, there's a 5 again.
Right. And a 3-by-3 grid, you count up all the 1-by-1s, the 2-by-2s, and the single 3-by-3, you get 14.
That's incredible.
It's the very same sequence appearing in a completely different context. I remember trying to count these as a kid. If only I'd known A00033302 back then, could have saved me some serious effort.
That really is amazing, the same numbers popping up like that. What is it suggest, about these numbers that they can manifest this way? Does this connection maybe hint at deeper structural properties? How they relate to other important number families?
Exactly. That's a great question. And yes, if we connect this to the bigger picture, these square pyramidal numbers are deeply intertwined with other important figurate numbers.
Like which ones?
For instance, an can actually be expressed as the sum of 2 consecutive tetrahedral numbers.
Oh, okay. The pyramid numbers built with triangles.
And this connection naturally raises an important question in number theory. Can a square pyramidal number itself also be a tetrahedral number? Or maybe even a perfect square?
Can it?
Well, surprisingly, it's quite rare. G.N. Watson proved something amazing, and it was later noted by Buchers and Top 2. The only square pyramidal number greater than 1 that is also a perfect square is 4900.
Just one?
Just one. Yeah. That's a 24. And even more restrictively, it turns out no square pyramidal number greater than 1 is also a tetrahedral number. It was a significant result, really demonstrating how unique and sometimes, well, rare these intersections between different types of figurate numbers can be.
That's a profound insight, showing how specific these relationships are. So beyond these connections, what other, maybe surprising, numerical patterns does A000330 reveal? For a number theory student, what really jumps out?
Well, beyond the visual elegance and the structural stuff, A00000330 reveals some really neat numerical patterns. Consider just the units digits of the sequence for n greater than 0.
The last digit.
Yeah, the last digit. They form a purely periodic cycle that repeats every 20 terms. It goes 1, 5, 0, 0, 5, 1, 0, 5, 5, 6, 0, 9, 5, 0, 6, 5, 9, 0, 0, and then it starts over.
A 20 cycle just from summing squares.
Exactly. It's not just a cool pattern. Understanding how these seemingly simple sums generate such complex yet predictable periodic structures is fundamental. It helps tackle deeper problems in number theory, like classifying other sequences or even touching on things like Waring's problem. It shows the unexpected reach of A000030.
That's a fantastic point, that interplay between simple definitions and complex outcomes. Are there any other specific properties that stand out?
Absolutely. There's another nice number-theoretic property. It turns out that n divides an if and only if n is congruent to plus or minus 1 modulo 6.
Meaning its remainder when divided by 6 is either 1 or 5.
Precisely. This specific divisibility rule links these numbers directly to modular arithmetic. It offers, a deeper insight into their behavior and how they interact with prime numbers and other number systems.
So from stacking cubes and counting squares in a grid to revealing hidden periodic patterns and these neat divisibility rules. OEIS A000030 is truly a versatile and fascinating number sequence, isn't it?
It really is.
It feels like it just pops up in the most unexpected and, well, beautiful places.
Indeed. And maybe to leave you with a provocative thought, there's actually a conjecture out there.
Oh.
It suggests that every integer, positive or negative, can be represented as the sum of just 3 generalized square pyramidal numbers.
Generalized. Meaning?
Generalized means we can apply the formula even to negative integer values of n. So we include a broader set of numbers derived from that same definition.
Sum of just 3 for any integer.
That's the conjecture.
Yeah.
So what does that imply for the richness and universality of these numbers? That they might, in some sense, form the building blocks for all integers. Definitely something to mull over until our next deep dive.